morning, everybody. Welcome to my presentation. I think key caveat to say from the off, this is a modeller's perspective from PSA. I don't purport to be a hazards expert. I'll just do a quick sense check. So, how many hazards people do we have in the room? Those external hazards? Hello, Peter. Mia, put your hand down. Okay, so I'm not going to get inundated with detailed hazards questions, hopefully, so that's a good thing. Okay, so what we're going to look at today. So, brief introduction, talk about the problem. I'm going to look into seismic events, what really happens in inverted commas. Then I'm going to look at modelling, and we've sort of got past, present and future. And then I'll get into closing remarks. So, Seismic PSA has been performed internationally for many years, primarily in the US, but it's something that I think if you've been involved in PSA, especially for a few years, and especially in the newer build area, you will see Seismic PSA floating around. It's a technique that's constantly evolving, so it started off quite simple and it's getting more and more complex. And you have disciplines such as geologists, seismologists, civil engineers, mechanical engineers, and of course, PSA engineers. Who might be the best, but I'm not going to dwell on that too much. The key thing is, when you've got all these different disciplines involved, it gets a little bit complex. And I think we're looking at I&C being complex and lots of uncertainty, and seismic is very much the same. So you start with something quite simple, looks like a nice process, then you start learning about things like soil structure interaction, Monte Carlo, eigenvalues, and it just becomes a bit of a mess. When I first saw that diagram, I thought it was Manhattan or something like that, but it's not. It's something completely different. I think the key thing is that as a PSA analyst, I've come into this from the side, I'm looking at this, and I'm trying to do what PSA analysts always try and do, and try and make that right cut between getting the right level of complexity in there, but not overdoing it. Trying to get something that is really understandable. And it is quite challenging in Seismic PSA, I would say. So I do what I've been taught, and you go back to the basics. What actually happens in a seismic event? So let's take a typical American PWR. Those of you who know your American PWRs might know this one, so don't shout out the name. I will not say it, even under torture or duress. And so regulate your plant. So you've got your MC operators working hard. You've also got local ops doing things like fuel control and looking at the electrics. So if you say you're going to have an epicenter event somewhere in the middle, somewhere deep down in the soil, what's going to happen? Well, if you're a very small event, nothing. Apparently hundreds upon thousands upon millions of events happen each year which actually aren't even detectable by measurements, never mind even people. So they're quite easy to analyse because nothing happens. You have a very large event, smoking crater. Again, easy to analyse, but we're really talking about the ones in the middle, so more like an in-betweener. So let's start it off. So sink the event in, start things rumbling along. First thing that happens almost certainly is that you're going to get a loss of grid or loss of offsite power. Hopefully you won't go dark because you'll have something like emergency generators or gas turbines, and hopefully batteries as well. Now at this point, your MC operators are definitely awake, and they're wondering what the heck's going on. So let's be nice to Homer, let's give him his power back. So the key thing is that now you've had a seismic event. Now this is not just your main problem. You can also have other initiating events that are caused as a result of the seismic event. So as we said, you lost your grid, but also within the core, you could have a problem with the way it all lines up. The complex word. So your rods might not actually go in. So that is a problem straight away because you've not even managed to achieve safe shutdown. You could also have problems in your core in terms of actually inducing a LOCA, so loss of coolant accident from a pipework breach, but also you get pipework breaches all around the plant. So you get a steam line break, feed water break in some sort of contaminated water is actually not a very good thing. Similarly, you can lose your cooling, so we'd call this a loose event, so loss of ultimate heat sink, and that's the same whether or not you've got a river site like this with cooling towers that can fall down, or whether you're actually on the sea itself. Similarly, you could actually crack your containment if you're in PWR space, but obviously AGR space, we're talking about your concrete pressure vessel, which is something you really don't want to happen either. And then once you've had the initiating event and you're going on, it doesn't really stop there. So there's a few Fukushima lessons, but it's not just specific to Fukushima. One of the classics is, and shown here really just by a road, you can't really depend on off-site help. Chances are that if you have an event big enough that really has given your reactor a good shake, the rest of the country is dealing with the same thing. So you can't expect lots of people to come off site and give you lots of help. One of the other things, flood, tsunami. Now, obviously, it's not going to happen absolutely everywhere. I know I'd not say that the key lesson for Fukushima is you're going to get tsunami following an earthquake. I think we knew that already. But the key thing is that something else is going to happen. It's going to happen not instantly, but sometime afterward. Aftershocks. You don't just get one seismic event, you get lots and lots of small tremors afterwards. And they can do lots of things. Primarily, they're a barrier to your local operators. So your operators are not necessarily going to be able to get from A to B the way they used to. When aftershocks happen, they're going to have to stop everything and get undercover. So that's going to really limit your local recovery opportunities. It doesn't stop there. You can also get local fires popping up. At the very least, it's going to distract your local ops. So you're going to have to put out the fire to get to what they're going to, or find ways around it. So these are all things that will really happen following a seismic event. Also, what's really going to happen? You're going to be there for a long time. So you've got no local infrastructure, so you may not be able to get on and off site necessarily. At worst, they'll fall asleep. More likely, they'll just get really stressed out and start making really bad decisions under fatigue and stress. And don't forget your components as well. We generally in PSA live in a 24-hour world. We know our components go for longer than that, but how long? How long do you run out of fuel? How long do your cooling water just overheat because the heat exchangers aren't being as efficient as they are during normal operation? All these things can all add up and really take us away from our nice, safe PSA area. So, okay, seismic events, we know they're a problem, but how serious a problem are they? So here's some stats, putting them all in context. The global and US ones are from the US Geological Society, UK British Geological Society, and Japan, the Japanese equivalent. Here we've got how many per annum. The key thing about this column is, apart from Japan, they're all ones that they say happen, but you don't feel. Japan, the 1500 district ones, it will actually go in the ground. Other than that, they're all directly comparable. So globally, the US estimates that there's over 1 million that happen. Quite a few of these they reckon they can't even detect, and obviously even more than that you can't even feel. The biggest one ever, 9.5 in Chile in 1960, and they estimate based on the stats you will get an 8 or stronger annually somewhere in the world. In the US, 9.2 in Alaska, 1964, and they get a typical strength of 6.9. These are all Richter scale, by the way. Japan is a 9, and that is the Honshu earthquake which led to Fukushima, and they get a typical of 6.3. For the UK, 6.1, that's the North Sea in 1930. Don't think anyone's around in this room who remembers that one. But typical annual strength is about 4. Now I could be flippant and say, well, we're not building nuclear reactors in the North Sea, so it's all fine. But the key thing is here is that they are a threat in the UK, but proportionally, and don't forget it's Richter scale, so we're looking at logarithmic here. Do we need to go into as much detail as the US and Japan are doing in terms of their modelling analysis based on what we are seeing, in terms of both the number, and these are ones that you probably can't even feel most of the time, and the average severity we're getting, never mind the ultimate severity, which is sort of their day-to-day, is our extreme event. So how do we model these things? In the past, / current present for certain reactors, it's been essentially deterministic. So I think from Ola's earlier question, there are lots of PSA people in the room, so I won't have to explain the inventory too much. General convention is when you get to a node, up is good, down is bad. And this is very, very simple in terms of control rods and cooling. Obviously, in real life, it's not more complicated. But generally, that's how we analyse all faults. And seismic events, in the past, deterministically, have been no different. But what we're going to focus on is really the fault trees that sit behind these functions here, because that's where it's a bit more interesting, to be honest. This is a presentation. And it is where you see the biggest differences. So, simple fault tree, system failure at the top. You have your random component failures here. So let's say 2-train system, component 1, component 2. You have your operator there. CCF, of course. Seismic event, that's a house event, we'll come back to that in a minute. And support systems. We're not going to drill into that too much, that's just for completeness, really. So what happens in this one, really, is that you have a house event, and those PSA models that cover know that's essentially a hard one or not. And what you say is, if your system of components is qualified to take the event you've seen, that doesn't trigger. However, if it isn't, this is triggered and it fails your tree. Simple binary 1 or 0. The present, so what we see a little bit more in existing PSAs, it's very similar, apart from the fact you have this extra component here. The key thing is that you're bringing in a basic event that is now looking at the fragility of that system to an event. So it's not 1 or 0, it's a conditional probability depending on the level of seismic event that you're seeing. The key thing I would say is that this is a system level one, and generally the data within that magic box is completely based on the weakest component within the system. And you could argue that's a little bit conservative. So what's in that box? Good question, that's what I want to know. So this is typical fragility curve. Along the bottom, you might not be able to see, but it's annual return frequency, going from quite frequent to infrequent, and failure probability at the side. That goes on a scale of 10 to the minus 49, quite improbable, to 1. Now, the key thing is, if you get a 10 to the minus 4 event, which is somewhere in the zone that we're thinking within design basis, for this sample component, the failure probability at that point is 8 times 10 to the minus 11. Now, the red curve is your 50%, so your median. Your green curve is 95th, and your blue curve is your 5th. And if you quickly read off, which I'll do, because my eyes are better and I'm closer, you're about 10 to the minus 16 at your 5th, and you're around about 10 to the minus 4, 10 to the minus 5 at your 95th. So that's pretty uncertain. 10 to the minus 11, you don't really care. More towards 10 to the minus 5, you probably do. Especially if you're looking at a system that's got a failure probability of around 10 to the minus 5. Step it up, taking a 10 to the minus 5 per year event. Suddenly, your 50 percentile is looking at 10 to the minus 2. Your 95th, you're tending towards 1, and your 5th isn't too clever at tending towards 10 to the minus 4. So for a 10 to the minus 5 system, that's giving you a big problem, and that's a single failure straight out. I think the key thing from this slide is that even within what we think we know within a component is very uncertain. And the analysis you're doing is only really as good as this. And this can be very, very simple and quite conservative. So the future, what could we do? So one of the ideas in my head, which I'm putting into practice at the moment, is independent failure. So you have your regular random failure, seismic event occurs, and you now clue in a component-based seismic event and a component, well, like a building-based seismic event as well. So the key thing is that this is conditional failure probability of your component or your building, assuming if your building fails, your component fails. That comes in, and that, if you like, goes under the logic of random failure. So the smart ones amongst you will notice there'll probably be a magical level by which you'll have an even distribution between your seismic and random failures, but generally you will see it will shift quite sharply depending on your level of seismic event. And you can do that copy and paste over how many components you've got in your train and combine it under whatever combination logic is appropriate for your system. So for a 2-train system, you would be doing this under AND logic. Now there is a problem with this approach, and especially for traditional models in the crowd, I'm pretty certain you'll spot what the problem is, and that is, traditionally the modelling is looked at saying seismic event across the whole site, you lose everything at the same time, no matter how many systems, because we're all seeing the same acceleration. That is called seismic correlation. It's something that is being looked at a lot more in depth, and it's something that kind of strikes at the heart at whether or not you're being very conservative or whether you want to be best estimate. So let's look into this a bit more. So component A, component B is exactly the same. We'll put them in the same building, and let's hit them with a seismic event. Now the key thing is both component A and component B are identical, and they're both qualified to take the seismic event I've just hit them with. So audience participation time. So what do we think happens? So any offers? Any offers at all? Nothing? I like that offer.
Both components work on the building fault now.
Nice, I like that one. Thinking outside the box, or right on the edge of the box, technically. Anything else?
Both fail because they've got the qualification wrong.
Possibly, very pessimistic cue, that's what I expect. The key thing is, but could one fail and not the other one, do we think? Think so? They're both qualified? If you're not convinced, what if this wasn't seismic? What if this was temperature? Let's say that they're qualified to take up to 50 degrees Celsius, they operate at 25, and the room temperature sneaks up to a cheeky 40 on a very warm day. Would you assume they both fail? Straight out?
No.
No. too conservative. So why is it different for a seismic event when they're qualified? And I think especially in the UK, this is a step from where things really weren't qualified traditionally to where we are now, where things are getting qualified, if not actually having it as part of their design basis. So you've got two things that could fail together, could not fail together, fail independently. How do you take account of there might be some common dependency? How do you do it generally in plant-based PSA? Common cause failure, thank you, Carl. Even in the US, they do common cause failure. And so that's what I propose. You can just have a seismic CCF. I thought this up on a day when I was thinking a lot about seismic, but it turns out I'm not the first person. There are a few papers where they have actually done seismic CCFs using the old beta factor model. And they've adapted the beta factor to take account of seismic similarities between the components. Currently, what's out there at the moment, from what I understand, is they are looking at actually doing proper deterministic assessments of the plant and giving you essentially like a beta factor as to how similar bits are. And you pay a seismic specialist probably an extortionate amount of money to do that across all your components. So it's something that at the moment hasn't got a great solution, but it's something I propose that we should be doing. In here as well as operator actions, I've not dwelled on the operator, so I apologise for HRA people in the room. Jasmine give me 40 minutes. I just about squeezed 20.
Just get on with it.
Yeah, see. So supportive. So the key thing is that you can just very simply switch in a seismic operator action, and that can take into account performance shaping factors to do with what they're seeing in a seismic event. So high stress, breathing apparatus, dodging fires, all those sort of things that you can take account of. And I think the HRA techniques we have in the UK are very good at accounting for that. So, quick pros and cons. So in the past, we had nice simple modelling, very quick to implement and aligned very nicely with the safety case. Some of the cons, diminished risk insights. I wouldn't say no, you do get some, because you can choose whether or not you want it to go off. And you can have a look and say, well, if I qualify a little bit more, what happens? But it's not real nice and precise. Overly conservative, almost certainly. Invisible, we'll talk about visibility in a minute. And similarly, there's no uncertainty in there. Present, so what we seem to be seeing more of. You're getting risk insights, but at a system level, still being quite conservative because it is system level only. A little bit more expensive because you're very dependent on spending money getting that data. And that can be quite expensive, especially if you have bespoke components and you can't borrow experience, if you like, from other plants. But it is visible. You are getting seismic minimal cut sets being generated. I think the key thing is that if you have a deterministic assessment that's nice, done at the time where you're building the plant, and you say, yeah, this will definitely take this level of earthquake. You do one or not on your PSA, you don't see cut sets, you keep going on. Now, PSA is not the main driver, and I think in the UK we generally are quite good at redoing assessments anyway. But if you've not got seismic cut sets coming up and keep telling you if it's still a problem, still not, in the context of your PSA, I think there is a danger that you're not going to go back to your deterministic assessment and say, hang on a minute, is this really true? And as a result, things might not get updated. In the future, key thing is here, you're getting some detailed risk insights, you're being more best estimate, but you are looking longer to implement, and it's going to be more expensive for the modelling to a certain extent, even though we have a tool that makes it quite quick, and you're still dependent very much on your data. Now, uncertainty. So all of these, you've got uncertainty being represented pretty much, but here's a little fly in the ointment. So post-Fukushima, you can't quite see it all necessarily, but here's an RCW pump, and they've assembled the whole system. That there is a person, so that gives you an idea of the rough scale, and this whole thing is a shaker table. This is all part of a JNES project, which some of you may or may not have heard of. So the key thing was, compared to earlier studies, they've assembled systems together and then shaken them. And for a comparative component, that similar graph we saw earlier, this is what we look like. So this is what we're looking at before. The graph is slightly different because it's more PGA than annual return frequency, but essentially it's the same. So these are our old little curves, and this is the new one. So it's quite extreme over to the right. And to give you a rough idea, what we're looking at here is probability up here goes from 1 to 0. And because it's not logarithmic, as soon as you see a little bit of lift off means you're going to see some quite high probability of failures. So here on the red one, you're seeing around about 1G. The JNES for the same component, you're not lifting off until around about 5. And that's a massive difference, especially when you're talking about peak ground acceleration in terms of G. So even though we've got some uncertainty here, and we think, oh, it could be this, could be that, latest best testing has taken us all the way over here. There are certain caveats on this. It is early data. There are certain things which don't make it completely comparable with this, but I think it's just worth noting that in terms of the context of uncertainty, it's not just within what you're thinking there, it's when you do something different, using different or more modern methods, it can really shake you up. So the future. So back to reality. I've talked about what the event really looks like. I think it's worth saying that I've not really talked an awful lot about aftershocks. So this is what you'll get roughly after a 5 on the Richter scale. You'll get one almost the same and lots of other quite strong ones. So how do you solve that? You could keep adding lots and lots of modelling. So you have aftershock 1, 2, 3, 4, 5 to the nth degree. But you're going to get a very complex model, plus how do you handle cumulative damage? That's always going to be a difficulty. Consequential hazards, so we talked about you could have a fire following a seismic event, could have a flood. You could take your seismic initiating event tree and put in conditional failure probabilities of things like water tanks failing due to seismic damage, gas cylinders breaching, giving you a fire, and then link those to your plant-based, if you like, or non-hazard, or external hazard, fire and flood modelling. That is possible, but there are lots of problems necessarily in how complicated you make this tree. But there are other things, longer term issues, so operator fatigue and stress, could do it with HEPS, again, quite difficult to do. Off-site incidents, what happens if you have an installation off-site that is struggling as a result of the seismic event that's going to come on-site and give you trouble. Fuel storage, I've not really dwelled on it, but obviously the fuel pond is essentially like a mini reactor, so that's just as important really. And I think, especially when we talk about long-term issues, it's something generic for PSA. We do struggle when we go beyond 24 hours. Uncertainty is a big part of that, but also things such as data. So, suggestions welcome. I'm pretty certain there are quite a few papers out there, and I've read a few of them, but it's something that, as a community, we do tend to struggle with. So, closing remarks. Assessment of seismic events, complex. I think we all know that. Almost as complex as INC. Original PSA modelling deterministic in nature, but it's increasing complexity. And we're getting, I would say, closer to realistic, in inverted commas, modelling. But we can, and I think some of the very quick examples I'll show you there, we can get something that's a bit more real, but it gets more complex. And I think the key message, if you're going to take one, at least from this presentation, is that we need to balance the realism and complexity. And that's not just for hazards PSA, that's PSA in general. It's one of the biggest problems with our industry that, and the way that it can really kill us off. You get a model that's so complicated, you can't understand it, very difficult to analyse the results, and it's a real pain to maintain, then it just, people are going to lose interest. And the key thing is that when you're coming from a more deterministic background and relying on the PSA, it should be permeable to a certain extent. And I think things like Seismic PSA can really stop that. And that's it. Thank you for your time.